A nuclear explosion could protect Earth from an asteroid impact catastrophe. We're talking about planetary protection here from incoming celestial bodies. Precise detonation of a nuclear bomb above an incoming chunk of space rock could be our best hope of avoiding a cataclysmic impact. That's assuming that these radiated chunks of debris from the explosion will not fall back on us. Now, a laboratory experiment conducted by an international team of researchers has confirmed that the X-rays emitted by a suitable sized atomic blast could shunt asteroids around 3 to 5 kilometers wide, about 2 to 3 miles off their course, taking them off their trajectory from Earth impact. While there's no evidence of a pressing need for such an anti-doomsday device, the consequences of being blindsided by a hazardous near-Earth asteroid are not trivial, making it vital we come up with a game plan that's guaranteed to save our skins. NASA recently demonstrated that if a heavy probe bumps a relatively petite pile of rock with enough force, it should steer clear of an impact with Earth. At just a little under 800 meters across and consisting of loose-bound gravel and boulders, the smaller member of the binary Dimorphos and Didymos system shifted far enough in its orbit to make astrophysicists confident in a directed collision could be used to nudge similar-sized objects into less dangerous trajectories. Of course, they didn't smash it with a nuclear device, they rammed it with a spacecraft. Now, as promising as the results are, it's also clear we need a lot more data before we can go throwing chunks of metal at any old asteroid in the hopes that it might avert disaster. A larger, more solid rock could be a whole other story. Luckily, there's more than one way to kick a mountain across the sky. Coupling it with a powerful fusion engine might work, for example, or using a focused laser to create a rocket effect by ablating the asteroid surface. Of the more feasible approaches, warming a small patch of the asteroid surface with an intense glow of radiation could also create a rocket effect, vaporizing minerals with such ferocity the escaping gases could, in theory, push the mass just enough to alter its path from impact with our Earth. Now, the basic principles behind evaporating rock with electromagnetic radiation can be tested and fine-tuned for different materials and mineral structures right here on Earth. Led by Nathan Moore, a physicist at Sandia National Laboratories in the US, researchers used a high-frequency electromagnetic wave generator called the Z-Pulsed Power Facility to squeeze 1.5 megajoules of X-ray out of a tank of argon gas. This bubble of radiation obliterated a thin piece of metal foil holding aloft a grain of fused silica, also known as quartz glass, leaving the sample hovering in free fall just long enough to resemble a tiny asteroid drifting through space. A fraction of a second later, the X-ray pulse washed over the target, stripping micrometers from its surface and generating shock waves that provided essential data. And this could be used to predict the effects of a significant larger burst of X-rays out in the interplanetary vacuum. In fact, the resulting transfer of momentum implies asteroids as large as 5 kilometers across could plausibly be moved using this approach. More detailed models, such as the radiation hydrodynamic model illustrated here and those in other studies, can be tested against experimental data acquired with this technique and used to refine the predictions for different asteroid intercept missions, the team notes in the report. Of course, asteroids are made of more than fused silica, often including a mix of volatiles piled up in a variety of ways. Using the same approach, each potential scenario could be tested without needing to put together expensive missions and waiting years to analyze the results. Ideally, it's knowledge we will never need, and though a handful of city-killer asteroids are predicted to come within a cosmic whisker of Earth. Nothing on the map promises to strike anytime soon. That's assuming we've seen everything out there, which we have not, of course. Still, nobody likes surprises. Should a bullet with our name on it come whizzing out of the darkness, we should know exactly how to take it back into oblivion. Was published in Nature Physics, and it's on Science Alert by Mike McRae. Please leave your comments, and thank you for your support. Support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.